The pigeonhole principle that we'll discuss in this video is fairly simple to state, but has surprisingly sophisticated applications. Here's how it's stated. It's a matter of putting a bunch of pigeons in pigeonholes, and if you have more pigeon than holes, some holes got to have at least 2 pigeons in it. I'll say it this way numerically: if a collection of n+1 things is put into n boxes, then there's a box with at least 2 things in it. Not at all surprising, but we'll see some curious things as we go through this. So let's take an example. Suppose we have a box with blue, green, yellow, red, orange, and white balls. How many would you have to draw without looking to be sure of getting at least 2 of the same color? Well, the thing here is that we have 1, 2, 3, 4, 5, 6 different colors of balls, and so these are our pigeonholes. And so if we have them labeled blue, green, yellow, I'm just going to abbreviate these last ones with first letters. So we have 1, 2, 3, 4, 5, 6. 6 n equals 6 pigeon holes. And when you're doing this, I would like to see your pigeonholes labeled so I understand what you're talking about. And so how many would we have to draw without looking to be sure we get at least 2 of the same color? Well, we'd need to have 1 more than the number of pigeonholes, 1 more than the number of colors. So we need to draw n+1, which is equal to 7. So that's the answer to that one. Now I'm going to ask you a little different one. This is kind of interesting. So in this one here, the claim is that a subset of 5 of the numbers from this set, so a subset of 5, size 5, will contain at least 1 pair that sums to 17. Wow. In fact, that should be a 16. So we'll make it that. That sums to 16. So let's see how that works out here. How could we make this arrange? How could we arrange this to solve it? Well, you notice that these do occur in pairs that sum to 16. So 1 and 15, 3 and 13, 5 and 11, and 7 and 9 all sum to 16. And notice there's 4 of those, and we're choosing 5 numbers. So you can see already why it's going to work out. But to make it fit into the scheme, and I want you to try to do this, I'm going to write down pigeonholes. This pigeonhole is for the numbers 1 and 15. This pigeonhole I'll label with a 3 and a 6 and a 13. The next one is labeled with a 5 and an 11, and finally a 7 and a 9. So if I choose a number from it, I'll just stick it in the appropriate box. So we have n equals 4 pigeonholes, and we'll select n +1 equals 5 numbers. So some pigeonhole has at least 2 which sum to 16. Yeah? So that's a way to do that kind of a problem here. But the idea is, identifying the pigeonholes very clearly. So another one, a function from the set consisting of the integers 1, 2, 3, etc. through 30 to the set B that just contains the lowercase English letters cannot be 1-to-1. Now remember, 1-to-1 means that 2 different inputs cannot have the same output. 2 different things from A cannot have the same letter assigned to them from B. So, remember how we can describe a function by putting like the domain here and the codomain, the things that it gets mapped to, over here. So the function itself could be described by saying, okay, what is the value, the function value of 1? So that would say f of 1 is c, if we name it f. And let's take 2 maybe to z. So f of 2 is z. And let's take 3 to b, 3 to a. I guess it went to a there. 3 to a, and I don't know, on and on and on. So other more arrows, and 30. I don't know. I mean, I could take it to anything here. I'll take it to z. F of 30 equals z. That's how a function would work. So the point is that there's no way we could make these assignments of the output for the given inputs without duplication, and the pigeons here would be the outputs A, B, C, all the way to Z. So there's 26, n equals 26 possible values or outputs. But we're going to be putting in here 30 inputs. So some output has 2 inputs, say x and let's use a and I don't know, let's use k and l for integers, right? 2 inputs, that is the word input here, hard to read. Inputs. So 2 inputs have the same output, meaning f of k equals f of l, and that's not one-to-one. Yeah? Okay. I think I will, yeah, let's go ahead and talk about ceiling and floor. Those are pretty quick. We're going to use them in the next one, but let's go ahead and talk about ceiling and floor. So the ceiling and floor functions are defined as following. First of all, the floor function of x is the largest integer less than or equal to x. So sometimes you may have heard this called the greatest integer function. We'll go ahead and call it the floor so we can talk about the floor and the ceiling function. So the floor function is an integer. It is less than or equal to x, and there is no integer between the floor function and x, no other integer. So it's the round down integer to an integer function. So the floor of pi is 3. The floor of minus pi, okay, now minus 3 is not less than or equal to pi, so this is actually minus 4. And the floor function of 7 is equal to 7. The ceiling function is defined as the smallest integer that is greater than or equal to x. It has to be at least as big as x, but there's no smaller number that satisfies that. So the ceiling function is the round up, and the ceiling function of pi is 4. The ceiling function of minus pi is minus 3. That's the next integer above it. And then the ceiling function of 7 is 7. Okay, we're going to use this in the general pigeonhole principle that I'll describe in the next video.